So in this video, we are going to finish up related rates by looking at one more example. And I think this example is a bit tricky, so I wanted to do a whole video where we kind of work through it using these 4 steps. If you haven't seen these 4 steps before, or you haven't seen the intro video for related rates yet, then go and watch those first because that'll make this video make a little more sense. So we are going to be solving this problem where we have a revolving light that is located 5 kilometers from a straight shoreline, and it turns at a constant angular speed of 3 radians per minute. With what speed is the spot of light moving along the shoreline when the beam makes an angle of 60 degrees with the shoreline? So this one's a bit trickier because we have these quantities like constant angular speed and lots of angles involved that we haven't really seen in related rates problems before. But even so, we can still use these basic steps over here to solve this problem. So the first thing that we're going to do is organize our information and start by drawing a picture. So let's see what our situation is like. We have some revolving light, so I'm just going to draw here. This is our light that is revolving, and this is located 5 kilometers from a straight shoreline. So this is going to be a distance of 5 from a shoreline that they tell us is straight. So we can assume that that shoreline is perfectly straight like that, and it turns at a constant angular speed of 3 radians per minute. And they want to know with what speed is a spot of light moving along the shore when the beam makes an angle of 60 degrees with the shoreline. So what they mean by this beam making an angle of 60 degrees is they're saying that this light beam is going off of the revolving light and hitting the shoreline, and when it hits the shoreline, that makes a 60-degree angle with the shoreline. Okay, and so we now need to figure out how we are going to label these other bits of information that they gave us. So we labeled that it was 5 kilometers from the shoreline. We labeled that the beam at the moment in question is going to make a 60-degree angle with the shoreline. And they also tell us that this is turning at a constant angular speed of 3 radians per minute. So we know that this is a rate of change because we have some quantity per another quantity. So that means we want to represent this value of 3 using differential notation. So we need to figure out how we are going to label, what symbols we're going to use to label radians and minutes. So what I'm going to do is I'm going to use theta to represent radians. That's pretty common. And then I'm going to use the letter T to represent time. And we know that time is in minutes because up here they said 3 radians per minute. So we know that we are measuring time in minutes. And so they told us that the constant angular speed was 3 radians per minute. So if we're going to represent this using differential notation, the thing that's changing is the radians, and it's changing with respect to time, to minutes. So if we use differential notation, we would say d theta over dt is equal to 3, because we're saying that this theta value is changing with respect to time. And so where on our picture would theta be? Well, they're saying that the revolving light is turning at a constant angular speed. So when they say theta, they are referring to this angle up here in this corner of the triangle. So this angle up here is theta, this one down here is 60, and then we have a right triangle, so that is just going to be a right angle. So this is the angle theta that is changing, and they told us that it is changing exactly at the moment in question. It is changing at 3 radians per minute. Okay, so it looks like we've labeled everything that we know, we've drawn our picture, and now the next step is to figure out what they're asking us to find. So they want to know with what speed is the spot of light moving along the shore. So what they mean by that is they say as this revolving light rotates, the beam is first going to get shot here, then the beam's going to get shot here, and then it's going to get shot here, and then it's going to get shot here, and so on, right? So the beam is traveling along the shoreline. So they want to know what that rate of change is. They want to know how the beam travels, how fast the beam travels along this shoreline. So what we need to do is we need to come up with some label for this horizontal distance, for the length of the shoreline. So I'm going to call the length of the shoreline x. And it doesn't have to be x, you can call it whatever you want. So the length of the shoreline is x, and they want to know at what speed the light beam travels along this shoreline. So if we were to use differential notation to represent that, we would be talking about, and I'm going to do it in blue, we would be talking about dx dt, right? How fast is this beam moving along this distance x with respect to time? That's what they mean by the beam moving along the shore. So they want us to find dx dt. So that's why this is going to get a box and is going to get stars next to it to remind us that we are trying to figure out dx dt. Okay, so now we have organized all of our information, we've drawn our picture, figured out what we're trying to find. So now the next step is to write the relevant equation. And so the relevant equation needs to relate the information that they've given to us with the information that we are trying to figure out. So we know that we're trying to find dx dt. So whatever equation we write better have the variable x in it, right? If it doesn't have the variable x in it, then when we differentiate it, dx dt isn't going to show up anywhere, and that won't be helpful to us. So we know our relevant equation needs to involve x. And so what other information have they given us? Well, they gave us this 5 right here, they gave us 60, but then they also told us that d theta dt was 3. So we are probably going to have to use theta. Theta is going to have to be involved in our relevant equation because they told us the rate of change of theta. Okay, so we know that we need x to be in our relevant equation and we need theta to be in our relevant equation. So can we come up with some equation where both theta and x show up in that equation? And so this is probably the trickiest part of this problem, is figuring out the equation to use. But what we are going to use, and you might have recognized it, is that we have a right triangle here, right? Because that angle right there is 90. So we can use right triangle trigonometry, right? Because like your SOHCAHTOA, your sine, cosine, tangent, those relate side lengths of right triangles with angles. So now we want to figure out, well, should we use sine, cosine, or tangent? And so let's see, if this is our angle theta, we want this value up here, x, to be involved. And if we were to use sine, we would need to know the opposite, which is going to be this x length over hypotenuse. But do we know the hypotenuse? No, it doesn't look like we know the hypotenuse, right? We don't have this side length labeled. So that kind of knocks out using sine. What about cosine? Well, cosine's adjacent over hypotenuse, so again, we'd run into that issue. What about tangent? Tangent is opposite over adjacent, right? And so if we write the equation using tangent, is going to be tangent of theta. So our angle is going to be theta because we need theta to be involved, right? We decided that. And so if we're doing tangent of theta, tangent is opposite over adjacent. So if this is our angle theta, the opposite side length is going to be that x. And then our adjacent side is this 5 right here. So this right here, tangent theta equals x over 5, is our relevant equation. And so now the next thing that we need to do is just differentiate it. So we are going to take the derivative of this, and don't forget that we are taking the derivative with respect to time. So we'll do this piece by piece. The derivative of tangent is going to be secant squared theta, and then we need to multiply that by the derivative of the inside, because theta is a function, right? Theta changes. As this light revolves, this angle theta is going to get bigger. So we need to treat theta like a function, which is why when we take the derivative, secant squared theta is going to get multiplied by d theta over dt. And so now we can do a similar thing when we take the derivative over here. We have the x divided by 5. We could pull out a 1/5 if we wanted to. And so we have the constant 1/5. And if we have a constant, just a number being multiplied by a function like x, and we're differentiating, that constant is just along for the ride. So that 1/5 is going to hang out front when we do the derivative. And then what's the derivative of x? And so it's really, really tempting to say 1 because you're super used to doing that. But remember, x is also a function, so we need to treat it like such when we're differentiating. Because over here we have x labeled as a distance from here to where the light beam is hitting the shoreline, and that distance is going to change as the light beam moves. So x is a function, so when we take the derivative of it, we are going to get dx over dt. t. So be really careful of that. It's really tempting to say the derivative of x is 1, but remember, x is not the independent variable. Okay, so we've differentiated, so now all we need to do is just plug and chug, right? So right here we have secant squared theta. Do we know what theta is? We don't have theta labeled over here anywhere, but can we figure it out? Because here we have a triangle, and we know that this angle is 90 degrees. We know that this angle is 60 degrees, and the angles, all the angles inside a triangle have to add up to 180, right? So if that's 90, that's 60, that means this angle theta right here has to be 30. So we know that theta has to be 30 degrees. But you still need to be really careful here, because it's probably tempting to go, okay, theta's 30 degrees, boom, I will just plug that in there for theta. But that is going to be an issue with our units, because look up here in the question. They told us that d theta dt was in radians per minute, right? Not degrees per minute. So if you were to plug 30 degrees in here for theta, but then you put 3 in for d theta dt, you would be having a units issue. You would be measuring your angles in 2 different ways. So you have to be consistent. You either have to convert d theta dt into degrees, or you have to take theta and convert that into radians. And we don't really have any way of converting d theta dt because that value was just given to us. So what we need to do is convert theta into radians before we plug it in. So hopefully you remember your unit circle, and 30 degrees is the same thing as pi over 6 radians. So that's really, really tricky. You need to make sure that your units match up with whatever units the question gave you. So we know now that theta is going to be pi over 6. So we're going to have secant squared of pi over 6, and that gets multiplied by d theta dt, which we know is just 3. And then that is all going to equal 1 over 5 times dx dt. So now we have an equation with only one unknown. Dx dt is our only unknown. And dx dt is exactly what we wanted to figure out. So from here, it is just going to be doing some algebra. So if you were to do secant pi over 6 squared, you were to throw that in your calculator, you would end up getting 4 thirds, and that's times 3. And then that is all equal to 1/5 dx dt. And so now if we multiply 3 by 4 thirds, you should get 12 thirds, which is the same thing as 4. So we are going to have 4 equals 1/5 times dx over dt. And now the last step is to just multiply both sides by 5. So we're going to get 20 equals dx dt, and that is exactly what we wanted to figure out. Now, what are the units going to be on this? So our units are going to be whatever our x units are divided by whatever our t units are. So x was this distance of the shoreline. So how are we measuring distance in this problem? Well, if we look up here, it said a revolving light was located 5 kilometers. So kilometers is how we are measuring distance. And then time is in minutes, right? Right here we have 3 radians per minute. So that is how we are measuring time. So that is our answer. 20 kilometers per minute is dx dt. So hopefully you can see that even though this one was a bit tricky in that the relevant equation is one that doesn't come up all that often in related rates, it's still the same basic process. So really try to find any process that works for you and that you're super consistent about it. And yeah, be careful of the units. That was probably one of the trickiest parts of this question, along with, I think, writing the relevant equation. So don't forget your right triangle trig. It may come up sometimes, like in this problem. So hopefully that was helpful. If you have any other kinds of problems or different concepts that have to do with related rates that you want to see done, make sure you leave those in the comments, and don't forget to subscribe.